Welcome to Tomorrow Unveiled.
Today we're diving deep into a central theme our dedicated research team has been tracking, something we're calling green code, hot core.
Right.
And look, this isn't some far-off concept. It's really the dynamic driving global energy strategy, like right now.
Absolutely. So let's unpack that for you. Green code. That's the digital economy's energy hunger, right? AI, massive data centers, the cloud.
Exactly. And it's relentless. It needs power constantly, 247, and it's growing incredibly fast.
Some of the analyses the team looked at suggest data centers alone could soon use as much electricity as, well, entire countries.
Yeah, it's staggering. And this huge non-stop power demand, it's forcing a major pivot towards what we're calling the hot core.
High-density, reliable, carbon-free sources. We're talking advanced fission, things like microreactors, and down the line, fusion energy.
And the key thing for you to grasp is that this isn't just about climate policy anymore. And that's part of it, sure.
But it's more immediate.
It's driven by hard-nosed corporate and military needs. The research compiled for Tomorrow Unveiled shows the last week, roughly October 16th to the 23rd, 2025, was really pivotal.
Oh, so?
We saw concrete engineering steps forward, big money commitments from the private sector, and crucially, firm government mandates.
Okay.
It feels like we've turned a corner. We've moved past arguing if advanced nuclear is possible, and now it's a scramble to figure out how soon we can actually build and deploy it at scale.
So our mission here on Tomorrow Unveiled is really to cut through all that noise for you, give you the shortcut to understanding how these technologies, fusion, fission, advanced nuclear, are shifting from just potential to, well, industrial reality.
Right.
And we thought we'd start with maybe the biggest leap, the one with the most revolutionary long-term potential. Fusion energy used to seem decades away, right?
Oh, absolutely. For maybe 70 years, fusion was mostly theoretical physics, lab experiments.
But that's changing.
Fundamentally, the data we've analyzed makes it clear. It's not really a science problem anymore. It's an engineering challenge. And it's got commercial contracts and roadmaps backing it up now.
Okay, so engineering challenges. When you talk about managing that plasma, that incredibly hot 100 million degrees soup, the recent progress is pretty amazing.
It really is. Let's talk about the UK Atomic Energy Authority, the UKEA, their massed upgrade facility.
Right.
The research team flagged a major achievement there. They managed the first ever complete, consistent suppression of these violent plasma bursts in a spherical tokamak.
Using 3D magnetic coils, I saw that?
Exactly. Three-dimensional magnetic coils.
Why is suppressing those bursts, those instabilities, so critical?
Well, they're called edge localized modes, or ELMs. And they're not small fluctuations. Think of them as massive, sudden heat pulses that basically slam into the reactor walls.
Ouch, that sounds bad for components.
It's terrible for commercial viability. Imagine running a power plant where essential parts are getting hit with these violent thermal shocks over and over. You'd have constant damage, shutdowns, repairs. It's a non-starter.
So how do the 3D coils fix it?
They create this sort of magnetic ripple. It's not perfectly smooth. This ripple stabilizes the plasma edge, letting excess energy kind of bleed off continuously instead of building up and erupting.
Ah, okay. Like a pressure release valve almost?
Sort of, yeah.
Yeah.
And solving ELMs, especially in a spherical tokamak, which is naturally more compact,
Right.
well, that could mean cheaper, faster to build reactors down the road,
Right.
like the UK's own STEP prototype they're planning.
So stability is one huge piece of the puzzle.
Crucial.
But then there's control. How do you keep this incredibly hot, unstable reaction going precisely where you want it continuously? The sources suggest humans aren't fast enough.
No way. That's where AI, specifically machine learning, becomes absolutely essential infrastructure.
Okay.
We saw a lot of focus in the research on the work between Commonwealth Fusion Systems, CFS, and Google DeepMind.
Using DeepMind's Torax platform.
Exactly. On the Spark reactor, the reaction speed needed is just phenomenal. Plasma conditions change based on thousands of factors, magnetic fields, density, temperature, all in milliseconds.
Humans can't possibly keep up with that.
Not a chance.
But hang on, using an evolving AI to control something so critical, are regulators okay with that? Is Torax like a constantly learning AI or more like a super fast assistant following set rules?
That's a really sharp question, and yeah, it's critical. The consensus from the materials we looked at is that Torax isn't some freewheeling AI making creative decisions.
Okay.
It's more like an incredibly fast predictive control loop. It anticipates how the plasma will behave milliseconds ahead and tells the magnetic control system how to adjust before things go wrong.
So it's faster correction based on predicting instability.
Precisely. It's that shift from human reaction to algorithmic anticipation that makes continuous grid-ready fusion seem possible. It's computational engineering now.
Right, so the engineering's moving fast. What about the money? You mentioned commercial contracts.
Yeah, and this is maybe the strongest signal that fusion is getting real. We're seeing actual power purchase agreements, PPAs, being signed.
For power that won't exist for years, right? Like the 2030s.
Exactly. CFS, for example, locked in a huge deal, $1 billion with the Italian energy giant Eni for power from their future ARC reactor.
Yeah.
Google also put capital in via a similar deal.
Wow. So big energy companies are betting real money on fusion delivering in the early 2030s.
That's the signal, yeah. They see it as a bankable asset, not science fiction. They're securing their future supply of high-density carbon-free power now. That shows real confidence the engineering hurdles will be cleared.
And governments are backing this up. I saw the U.S. Department of Energy released a roadmap.
They did, a comprehensive national fusion roadmap, also targeting mid-2030s commercialization.
Does it just say, go build fusion, or is it more specific?
Oh, it's very specific. It builds on the $9 billion plus in private money already invested, and it clearly identifies 6 critical gap areas that need solving.
Engineering gaps.
Pure engineering and materials science gaps. And connecting the dots across the research, the single biggest one is materials, specifically dealing with neutron bombardment.
We talked about reactor walls getting damaged. That's the neutron.
High-energy neutrons, yeah. In a commercial fusion reactor, they constantly hit the surrounding structures. Over time, this weakens materials, makes them swell, brittle.
So you need materials that can just take that punishment for years.
Exactly. If you don't have materials that can survive, you're constantly replacing the reactor's insides, which is incredibly expensive and complex. The DOE roadmap highlights this as the major challenge needing massive public-private focus between now and, say, 2035.
It's the checklist to get from lab experiment to power plant.
Pretty much. It shifts the question from can we get plasma hot enough to can we build a structure that lasts.
Meanwhile, in Europe, they're already thinking about the industrial scale-up with this Gauss Fusion plan.
Yeah, the GIGA blueprint. It's for a stellarator type of fusion plant.
Stellarator.
Yeah.
Different design, more complex magnets, but potentially steadier operation.
That's the idea. And this Gauss report, it's like 1,000 pages long. It's remarkable because it moves beyond the physics entirely.
And into the nuts and bolts.
Totally. It's an industrial plan. How do you build the supply chain? What's the construction schedule? How do you handle safety regulations? What does it actually cost to operate?
They put a number on it.
Yeah, the estimate for the first plant is around 15 to 18 billion euros. It's a huge number, but it shows they're serious.
Targeting the mid-2040s, Europe is planning for fusion as a massive, real-world industrial project.
Okay, so fusion is the long game, getting real, but maybe still a decade plus out for major impact.
Right.
But fission, especially these smaller reactors, SMRs and microreactors, that seems to be moving much, much faster.
It is. The timelines are way more aggressive. And interestingly, the big drivers aren't traditional power companies.
Who is it then?
According to the research team's synthesis, it's really 2 groups pushing the pace: big tech and the military.
Let's start with big tech. Amazon's name came up a lot. Yeah, Amazon's commitment to use X-Energy's X100 reactors. These are high-temperature gas-cooled SMRs at a facility in Washington State. That's kind of the poster child for this trend.
So we're talking.
The first phase is 4 80-megawatt electric units, so 320 megawatts total. But the site can apparently scale up to 12 units, almost a gigawatt.
A gigawatt. That's a serious power plant, and it's just for Amazon's data centers and AI.
Primarily, yes. It feeds directly into that green code demand we talked about. They need massive, reliable, carbon-free power, and they need it now.
And they're funding it differently, not like a normal utility project.
That's the really disruptive part. Traditional utility bills are slow, bureaucratic, lots of regulatory hurdles. Amazon is basically bypassing a lot of that.
How?
By guaranteeing they'll buy the power long-term through these power purchase agreements. They're essentially underwriting the project directly.
So that gives the reactor company X-Energy the financial certainty they need, reduces the risk for banks and investors.
Exactly. It dramatically speeds things up compared to waiting for a utility commission to approve everything.
But what does that mean for the market? And maybe are there downsides?
Well, the upside, highlighted in the financial data we saw, is speed and volume. This direct corporate funding gets reactors built potentially years faster.
Okay.
And it guarantees orders, which helps vendors justify building the factories needed for mass production. The research team pointed to this Amazon deal potentially anchoring a $50 billion plus pipeline for SMRs. That's huge.
And the downside, less public oversight, maybe?
That's the potential risk, yeah.
Yeah.
These projects are laser-focused on corporate needs, which might mean less public input than a traditional utility project might have. Something to watch.
Okay, so corporate demand provides scale. You said the military provides the timeline push.
Yes, through the U.S. Army's Janus program. This is all about speed and certainty.
What's the goal of Janus?
Resilience. Plain and simple. They want to deploy commercially owned and operated microreactors on military bases here in the U.S.
Why? Power outages, cyber threats.
All of the above. The idea is for critical bases to be able to island themselves, run independently from the main power grid if it goes down or is attacked. It's a national security priority.
And the timeline is tight.
Unprecedentedly tight.
Yeah.
There's an executive order, 114299, that mandates the first Janus reactor must be operational by September 30th, 2028.
2028, that's less than 3 years from now, as of late 2025. For a nuclear project in the U.S., that sounds impossible.
Under the old ways of doing things, it probably would be. And that's kind of the point.
What do you mean?
It acts as industrial policy. This incredibly aggressive deadline forces the Nuclear Regulatory Commission to figure out how to streamline approvals for these standardized factory-built designs.
It forces the system to adapt.
Right. And by guaranteeing that first customer, the Army de-risks the whole thing for the commercial market. It helps companies like Radiant. They're building a microreactor factory in Tennessee.
Planning 50 units a year, I read?
Yeah, their little 1 MW Kaleidos reactor. The Janus program helps create that initial stable demand needed to get the factory model rolling for everyone else.
So the U.S. is pushing hard with corporate and military demand. But it's a global race, right? Who's ahead right now?
Well, in terms of getting the first advanced modular reactor actually connected to the grid, the data clearly points to China.
Which reactor?
Their ACP-100 SMR, they call it Linglong One, they just completed cold functional tests.
Meaning?
Meaning it's basically assembled and they're testing systems before loading fuel. It positions them for grid connection, likely in the 2026-2027 timeframe.
So China will likely be the first to operate this class of reactor.
Looks that way. And that's a big deal. They'll get real-world operating data, construction experience, cost insights, years ahead of Western competitors, potentially.
That must put pressure on companies like Rolls-Royce SMR in Europe.
Absolutely. And you see them responding. Rolls-Royce SMR just announced this big supplier technical briefing event in Prague.
What does that signal?
It signals they're moving past design and focusing squarely on manufacturing. They're lining up the companies that will actually build the components.
Because the whole SMR idea relies on factory production, right? Like building planes, not cathedrals.
Exactly. You need that robust cross-border supply chain to crank these things out efficiently and bring the costs down. Rolls-Royce is actively building that European industrial team now. The bottleneck is shifting from design to manufacturing.
Okay, this is fascinating stuff. Before we dig into how these new reactors tackle the big historical challenges of nuclear fuel, waste, safety, let's just take a quick moment. If you're finding Tomorrow Unveiled insightful.
Yeah, and you're watching on YouTube, please do take a second to like the video, subscribe to Tomorrow Unveiled, maybe hit that new hype button. It really helps more people find us. And turn on notifications so you don't miss future updates.
And if you're listening on a podcast service, maybe Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave Tomorrow Unveiled a rating and a review. It genuinely helps us reach new listeners.
We do love hearing what you think, too. So whether you're on YouTube or your podcast app, drop a comment. Let us know your thoughts on this huge pivot towards high-density energy we're discussing.
All right, let's talk about the elephant in the room for nuclear power historically. Waste and safety.
Right. Decades of debate there.
But the sources our research team analyzed suggest this new generation, the SMRs, the advanced reactors, they're designed differently. They tackle these issues head on.
Head on, yeah. It's not an afterthought. It's often central to the design and even the business model. Hashtag TAG 2.1, the waste to value proposition. Fast reactors.
Okay, how so? Let's start with waste. I saw mention of a big partnership, Oklo, Nucleo, Blycala, focusing on fuel for fast reactors.
Yes, a $2 billion strategic partnership. And it's aimed squarely at building the infrastructure for advanced fuels, specifically for fast spectrum reactors. These are often cooled by liquid metal, like sodium or lead.
Fast reactors, we hear that term. What makes them different regarding waste?
It comes down to the neutrons they use. Conventional reactors use slow thermal neutrons. Fast reactors use high-energy, fast neutrons.
And why does that matter?
Because those high-energy neutrons can do something amazing called transmutation, They can actually split the really problematic stuff in conventional spent fuel.
Problematic stuff meaning?
The long-lived actinides, things like plutonium, americium, neptunium, these are the components that stay highly radioactive for tens or hundreds of thousands of years.
Okay.
Fast neutrons can fission these actinides, effectively burning them up.
So you're turning long-term waste into more energy.
Precisely. It hits two birds with one stone. First, you get way more energy out of the original uranium fuel. The analyses suggest potentially up to 200 times more. You're reusing what we currently call waste.
Wow, 200 times.
And second, by transmuting those long-lived actinides, you drastically reduce the radioactive lifetime of the remaining waste. Instead of worrying about 100,000 years or more, you're probably about maybe 300 years.
That's a completely different proposition.
It's a game changer. It shifts nuclear from having a massive long-term waste problem to potentially having a waste-to-value stream. That fundamentally changes the economics and potentially public acceptance. Hashtag 3.2, inherent safety and new fuel forms.
Okay, so that addresses waste. What about safety? The Amazon reactor, the X100, uses something called Treso fuel.
Right, Treso fuel, and this is key to the enhanced safety profile of many advanced reactors.
What is it exactly?
Treso stands for tristructural isotropic.
Yeah.
Think of it like a tiny radioactive seed, a kernel of uranium fuel,
Okay.
encased in multiple protective layers, carbon layers, and then a super tough layer of silicon carbide ceramic. Each tiny particle, smaller than a poppy seed, is its own miniature containment vessel.
How does that make the reactor safer?
Because the fuel literally cannot melt down in the traditional sense. That ceramic coating is incredibly robust. It maintains its integrity even at temperatures way, way above normal operation over 1600 degrees Celsius.
So even if you lost all cooling...
Even in a worst-case loss of coolant scenario, the reactor's passive cooling features would kick in. The core would heat up, but the fuel particles themselves wouldn't melt and release fission products. The integrity holds.
They call it meltdown-proof by design.
That's the term often used, yeah. Or walk-away safe. And this inherent safety has huge implications.
Right.
It means you potentially don't need the massive, complex, and very expensive active safety systems in huge concrete containment domes that older reactors require. That simplification is a major driver of lower costs and faster construction for SMRs.
Makes sense. But if lots of these reactors are coming online, you need a reliable supply of this special fuel.
Absolutely critical. And avoiding reliance on Russia for advanced fuel components like HGLU, high-assay, low-enriched uranium is a major push.
So efforts are underway.
Yes, the DOE has its fuel line pilot program, selecting companies to ramp up production. And you see joint ventures like Framatome and Standard Nuclear, specifically aiming to scale up trisoparticle manufacturing. Building that secure fuel supply chain is vital for this whole SMR deployment plan.
Okay, so fission and fusion are the nuclear side of the hot core. But the research also highlighted another contender for 247 clean power, right? Enhanced geothermal.
Yes, EGS-enhanced geothermal systems. It's about tapping into the Earth's own internal heat, which is obviously a massive constant resource.
But geothermal usually needs specific locations, like volcanic areas.
Traditional geothermal, yes. EGS aims to make geothermal viable almost anywhere by drilling much deeper to reach consistently high temperatures.
And new drilling tech is key here. I saw something about microwaves.
Millimeter wave drilling, yeah. Companies like Quasi Energy are pioneering this. Instead of grinding rock with a physical drill bit, they use powerful microwave beams generated by devices called gyrotrons to literally vaporize the rock.
Vaporize it.
Yeah. It potentially allows drilling much faster and, crucially, much deeper, maybe 10, 20 kilometers down than conventional methods, especially through hard basement rock.
And reaching those depths unlocks heat anywhere.
That's the goal. Consistent, high-temperature heat accessible globally, providing reliable 24/7 baseload power.
And can the existing oil and gas industry play a role here? The skills, the equipment.
Huge potential synergy there. The drilling expertise, reservoir management, handling high pressures deep underground, a lot of that knowledge is directly transferable from oil and gas to deep geothermal.
So it offers a transition path for workers and leverages existing infrastructure.
Exactly. That's a key part of the EGS appeal. It's not starting entirely from scratch. It can build on decades of experience, potentially accelerating deployment.
So we're seeing this big push towards high-density, hot core, energy nuclear, deep geothermal. But this is happening while renewables are also growing, right?
Absolutely. And it's important to acknowledge that the research team confirmed a really significant milestone just happened.
What was that?
In the first half of 2025, Globally, renewable electricity sources actually generated more power than coal for the first time ever recorded.
Wow, that is huge.
It is. And solar growth was incredible. It met something like 83% of the entire global increase in electricity demand. So progress on decarbonization via renewables is definitely happening.
But there's a but, isn't there? Especially relating back to that green code demand.
There is a divergence, yes. That aggregate success story hides some system-level challenges.
Like intermittency.
Exactly. Solar and wind are fantastic bulk energy providers when the sun shines or the wind blows. But data centers, AI, modern industry, they need power constantly. Perfectly stable power.
Which renewables alone can't guarantee without massive storage.
Right. You need enormous overbuilding of capacity to cover lulls, which leads to curtailment, basically throwing away clean power when you generate too much. And you need huge amounts of long-duration energy storage, which is still expensive and not widely deployed at grid scale.
So it creates grid management challenges.
Big ones. And economic uncertainty, too, it seems. The research pointed out the International Energy Agency, the IEA, recently had to cut its 5-year forecast for offshore wind growth.
By how much?
By over 25%. That's a significant downward revision.
Why? Costs. Supply chains.
Both. Rising interest rates, material cost inflation, especially for things like steel used in turbines, and complex supply chain bottlenecks for these massive offshore projects.
So while nuclear seems to be getting more policy certainty, think Janus, Amazon's funding large-scale renewables are facing more economic uncertainty.
That's the divergence the data suggests, yes. Predictability and certainty are becoming increasingly valuable, especially for attracting the massive capital needed.
Let's talk density again. We keep using the word, but the numbers are stark, right? Land use, for example.
Incredibly stark. This is becoming a real issue. Where do you put all these energy facilities? The data compiled for Tomorrow Unveiled shows nuclear has a massive advantage here.
How much smaller is the footprint?
Compared to utility-scale solar farms providing the same continuous power output, nuclear can use up to 31 times less land. Compared to wind farms, it's up to 173 times less land.
173 times.
Yeah. Think about the land area or sea area needed for a huge wind farm. The equivalent nuclear plant might fit on a relatively small campus. That matters for siting, permits, environmental impact.
And that density links directly back to reliability, the core value for the green code.
Absolutely. It's the capacity factor. Solar and wind might average 25–35% capacity factor over a year, producing power maybe a third of the time.
Okay.
Advanced fission and fusion designs. They're engineered for 90% or higher capacity factors. They run almost constantly, providing that firm, stable baseload power regardless of the weather.
Which is exactly what big tech and other critical infrastructure need.
And why they're increasingly willing to pay a premium or even fund the projects directly to guarantee that reliable supply.
Yeah.
#tag outro, #tag 5.1, and key takeaways and timelines.
Okay, so wrapping up this deep dive on Tomorrow Unveiled, the big takeaway really seems to be that this green code hot core idea isn't theoretical anymore. It's happening now.
Yeah, the demand from tech and the mandates from defense are accelerating advanced nuclear deployment faster than almost anyone predicted just a few years ago.
And we're seeing two distinct timelines playing out.
Seems that way. We've got Speed 1, which is the near-term stuff, advanced fission, SMRs, microreactors.
Timelines there.
China's Linglong One aiming for grid connection around 2026-27. The U.S. Army's Janus program demanding operation by late 2028. And then wider fleet deployment, driven by companies like Amazon, really kicking off in the early 2030s.
And then there's Speed 2.
That's the longer-term, high-reward play. Fusion. With the recent engineering progress in those big contracts, it's now a serious engineering target. The U.S. DOE is aiming for mid-2030s commercialization. Europe's big industrial plant, GIGA, looks towards the mid-2040s.
So huge momentum, but challenges remain, obviously.
Oh, absolutely. These aren't science challenges anymore. They're industrial challenges.
Yeah. Scaling
up specialized supply chains, making enough advanced fuel like HALEU and Treso, getting the regulations efficient enough to handle factory-built standardized reactors. These are the hurdles now. #tag 5.2, final provocation.
You know, the massive energy thirst of AI and the whole digital economy, it's often painted as a climate problem, right? A huge new source of demand.
Understandably so, yeah.
But listening to all this, it makes you wonder, could it be the opposite? Could this specific, relentless, absolutely inelastic demand for high-quality 147 power, could that be the very thing the nuclear industry needed? The catalyst to finally mobilize the money, the political will, the industrial scale to actually solve these high-density, clean energy challenges for good?
That's a really interesting thought. that the problem might actually contain its own solution by forcing our hand on these advanced technologies. Something for you, our listeners, to definitely chew on.
A compelling idea. We'd love to hear what you think. Whether you're on YouTube or your podcast app, leave a comment. Let us know your take on this massive shift towards high-density energy.
Thank you for joining us for this deep dive into the energy landscape.
We'll see you next time on Tomorrow Unveiled.